Hello, hi everyone. So to be transparent with you, I had already recorded this video, but um, for me, I record these videos on my laptop. It's a gaming laptop, and I usually put my laptop on performance mode. Well, today I didn't put my laptop on performance mode, so the audio, while fine, the video is super bad. It's very low FPS. So what I've decided to do is just to re-record with the same audio so as to not, do undo the work that I already did, but obviously it's live, right? I'm here, so we're kind of just gonna be hearing me talk. I'm gonna be hearing me talk along with you guys, and we're gonna go ahead and just go over some of the work that I already did, and I'll try to mimic most of my results. So let's go ahead and I'm gonna play the video now. So like for example, I'm talking and then you hear hello, hello, hi. So like it's, just being transparent about the whole situation. Okay? All right, let's get started to hearing me talk. Everyone, welcome to day 3. Let's get started. Today we're going to do partial fraction decompositions within integration. And then we're going to do some numerical approximations. So we have about 4 pages of notes to make. Let's get started right away. So partial fraction decomposition is something that we are coming into the woods with you learning it in pre-cal, assuming you learning it in pre-cal, excuse me. But I just put this quick little reminder, and you can sort of catch up in this way as well. Okay? So first, make sure the integrand is a proper rational function. If the degree of the numerator is less than the degree of the denominator, we move to step 2. If the degree of the numerator is greater than or equal to the degree of the denominator, we divide it first, then continue. Step 2. Factor the denominator completely into linear and or irreducible factors. Linear factors look like this. Key linear factors just have a power attached to them. Irreducible quadratics that you can't factor look something like this. Set up the partial fraction decomposition. Use the correct form for each type of factor. So if you see an x minus a, then your partial fraction decomposition will have this term. If you see a repeated linear factor, then you'll see a repeat of these terms. If you have n powers, then you'll have n terms. If there's a quadratic that's irreducible, then you'll have this term. If there's a quadratic factor that is repeated, then you will have one set of linear numerators for each time the quadratic is repeated. Step 4. Solve for the constants. Set up a system of equations. Step 5. Rewrite the integral as a sum of simpler integrals and integrate them term by term. Number 6. Combine results and add the constant. So for example here, we see that this bottom part can be reduced to two linear factors, x minus 1 and x plus 2. So we see two linear factors. This tells us that this fraction here, 3x plus 1 over x plus 1, or sorry, x minus 1, x plus 2 can be written as sum a over x minus 1 plus sum b over x plus 2. But how do you get these terms specifically? How do we figure out actually how you get A and B? Random, super random. I'm not used to being back on camera, so I was completely ignoring the screen. So I apologize for that. So for context, um, I was doing so I got used to just, looking like this. You can see me just like going zombie mode about it, but then I'm like, well, I need to interact with you guys, since I'm back on camera now, which I'm probably overcompensating with in this video, but we gotta do what we gotta do. Or I bet you're maybe you're like in the comments like you ignore the screen all the time. I don't intend to ignore the screen all the time, but I know like with recording those other two videos, I got pretty used to just being faceless. But now my face is here. So how do you get that A and B? Well, we divide the denominator on both the left and the right hand side. So you
Multiply, not
get
divide.
3x plus 1 is equal to
Silly me.
this whole expression multiplied here, which really, because of canceling out, just leaves the x plus 2 term. And this whole expression multiply this, which just leaves the x minus 1 term. Shifting the a, we got ax plus 2a. Shifting the b, we got bx minus b. And all of this is equal to 3x plus 1. Now, all of these numbers are, all of these letters are strictly going to be numbers. We can take advantage of that fact. So that means that whatever a plus b of the x's is, that has to explicitly be 3. And similarly with just the numeric constants, 2a minus b has to be equal to 1. So we can set this up into a system. We have a plus b is equal to 3, and we have 2b minus b is equal to 1. Therefore, we can choose to solve for either a or b. I'm going to go ahead and choose to solve for a, since these b's will clearly cancel out. And I'll have, oh, sorry, I wrote b twice here.
I was
So
like, I do
I'll
remember this.
write 3a is equal to 4. In the case where 3a is equal to 4, that means a is just simply 4 over 3. And then we can use one of these guys to just solve for b. I'm going to use this guy since I'm probably going to have a mixed fraction. 4 over 3 plus b is equal to 3. So subtracting that, or writing it as 9 over 3, you'll get 5 over 3. Then after getting 5 over 3, you can plug it into here.
If you want to see it the other
4
way.
over 3 over x minus 1 plus
So we plug
5
in
over
here.
3 over x
To be this A and
plus
that's B.
2. Then from here, you can go back to the integral. Because remember, all of this was work just to simplify this part. And now you can go back to the integral itself and write it as 4 over 3 over x minus 1 plus 5 over 3 over x plus 2, all integrated with respect to x. Then from here, you go ahead and, excuse me, then from here, you go ahead and do the integral. I'm going to skip the u substitution portion of this problem, but we know that we're doing u to be x minus 1, so du is dx. And similarly, we know we're doing u to be x plus 2, so du is dx.
I agree. I agree with myself.
So it leaves me with, I guess I'll do it like this. I was going to do the definite integral format, but we technically don't have to. 4 over 3 ln of x minus 1. Here, I need to start doing the absolute values because I saw in your homework you did absolute values. It's a
Yeah,
force of
I've been
habit to
noticing
just
that
not
I
include them,
forgot to put the absolute
so
values.
that's
That's
my
my
bad.
bad.
Plus 5 over 3 of x plus 2. And then we need to do plus c. So there's nothing really to simplify here. You could sure take out the common factor of 1 over 3, but reality that doesn't really help us too much. But that would be your final answer. The bigger difficulty of this problem lies in this part, in this color, in this red color. Let's go ahead and move on to this next page. So this next page has the issue where that bottom part is a repeated linear factor. So that means that our decomposition of this middle part, x plus 2 over x minus 1 squared, will be one constant over x minus 1 plus another constant over x minus 1 squared. Then, after that, go ahead and do the trick I told you where you multiply both sides by that denominator. You'll get
Multiply.
x
I said it
plus
right this
2
time.
is equal to a
Watching
times
myself.
1 of the x minus 1s, and then this b will just be by itself. You can mess with this a little bit, but we are able to do the same trick, where because these letters are just numeric values and not variables, you could set the a to be equal to the coefficient of this x. So a is equal to 1, which technically already solves your linear system. But let's do the more formal notation. Negative a plus b now also needs to equal 2. Well, like I said, this already spoils it for you, which isn't, oh no, we have an easy problem. Well, okay, that sounds rude. It's not that we have an easy problem, right? But we have an easy setup, right?
Yes,
Sorry,
not
I
an
hope that
easy
didn't sound
problem.
rude.
It's just it's an easier setup.
It's
We have an
alright.
easier time with the linear system
Okay,
versus what we
so
previously had.
we know a is 1, so we can just plug it in. Negative a plus b is equal to 2. B then is equal to 3. So then you could split this up to be 1 over x minus 1. And then you'll split this up to be 3 over x minus 1 squared. So now we go back into this integral here and we plug it in. So we get integral of parentheses 1 over x minus 1 plus 3 over x minus 1 squared dx. Then, I'm not, okay, I'm gonna skip this U substitution. I'm not gonna skip this U substitution just because this one is not as obvious. So you'll have ln of x minus 1 and then plus the integral of 3 over x minus 1 squared dx. So the U substitution for this guy is still x minus 1 and du is still dx. So you have 3 over u squared du, and then you're going to go ahead and get the answer of, hold on, I'm trying to do it too much mentally. That sounds that sounds like everyday struggle. No, I mean like I'm trying to do the power rule mentally, but I might as well just write it out and then go ahead and manually add it. So 1 negative negative 2 plus 1 is negative 1, negative 1. This will simplify into negative 3, 1 over u, which if we plug in back u and tidy this up a little bit, we'll get x minus 1. So our final answer will include
Bring down to ln.
this ln of x minus 1, and then we add the plus c, the constant for integration.
And plus c.
And then, oh, sorry. And that's going to be it. All right. Let's keep it going, because now we have a simple looking linear factor, but it's a bit different now. We have that negative 3 over x times x squared plus 1 has both a linear factor and a quadratic factor. So the setup is using one linear factor and then quadratic factor, which is bx plus c. Remember, it's the usage of two items on the numerator, one being next to an x and the other just being a constant.
Oh, sorry, numerator. So bx plus c. That's what I'm saying. I'm saying
Squared.
explicitly that because we're dealing with the quadratic, we have two things on the numerator. Just to
Then
recap.
from here, go ahead and multiply by the denominator. We get -3 is equal to a times x squared plus 1
Because the x's cancel out.
plus bx plus c. I'm going to put this all in parentheses. Multiply by x. Just to make sure that I'm properly knowing that the whole thing is being multiplied by x. This needs to do some distribution, so we have ax squared plus a plus b x squared plus cx. And then we have that all of it is equal to -3. Similar ideas here, just with an x squared included. There's no x squared term on the left, so that means a plus b must somehow equal 0. That c must also somehow equal 0.
Because there's no x term on the left.
And then the a, because it's the only numeric term, must equal -3. So if c is equal to 0 and a is equal to -3, we just have to solve for b, which we can see mentally it's going to be just a positive 3.
Because a plus b is equal to 0.
Okay. I just thought of something funny. So then we can split this up to be -3 over x plus 3x over x squared plus 1. We could do plus c. I say that in air quotes, but in reality, c is 0. So I don't really have to include it. You could include it just to keep like proper notations and whatnot, but in reality,
You could.
it's not really serving you.
It's not really serving you.
So now let's split up. This was all work just for this inside part. So let's actually do the question, which is the integration. So I have -3 over x plus 3x over x squared plus 1 dx. From here, I'm going to cheese this one a little bit and just do the integral right away. It's going to be -3 ln of x. This one, I want to just do the substitution out loud just so we don't miss anything. If u is x squared plus 1, then du is 2x dx. And then we see that there's no multiplicative of 2, so we have to take it out. So 1 over 2 du is equal to x dx. So you're left with a 3 over 2 integral of 1 over u du.
So that replaces u,
which you get as ln
so I'm going to place d
of u.
x.
And then you plug in back u.
Here, I pause the video. So then afterwards, you do the integration. You get ln of u. And then the last step would just be plugging back u.
Squared plus 1. We put back the ln here, -3 ln of x. And then we add plus c.
Look at that, plus c.
And that's going to be the answer. Oh, I keep forgetting.
Absolute value. Yeah, keep forgetting to do absolute values.
Okay. All right. So, moving on to another problem where there's two increases of difficulty. First increase of difficulty is that the bottom part is not factored for you. The second increase of difficulty has to do with that step 1 warning. The warning, I'll read it again, was if the degree of the numerator is less than degree of denominator, continue step 2. A degree of numerator is greater than or equal to degree of denominator, do long division first. We must do long division first in order to get this fully out. So let's do long division first. Here, do a different color to denote that. I'll put it here. X squared plus x3 plus 3x
Sorry.
squared plus 2x plus 1. So we can multiply this leading term by x and make it look like x to the power of 3, which make this guy look like x squared. Subtract it. We get left with 2x squared. I'm going to drag down this term plus 2x. We know that we can make this look like this just by multiplying it by 2. So we have 2x squared plus 2x. Subtracting that, we actually end up with both zeros, and then all that's left is a 1. So, like any long division, you have what's fully quotient out in your remainder. So this expression, 3 x to the power of 3, not 3x, plus 3x squared plus 2x plus 1, all over x squared plus x is equal to x plus 2 plus the remainder 1 over x squared plus x. All right, so that's pretty much it for this one. Now we have to do, actually let me write it out just so we don't get lost. Go to the integral of x plus 2 plus 1 over x squared plus x dx. So this part of the integral is pretty straightforward. In
This
fact,
part.
I'm going to do it right now. It's simply just going to be x squared over 2 plus 2x. But we still have to do this part of the integral, which we can do by splitting up this into being a linear term. We know that we can split up x squared plus x into
X times x
x
plus
times
1.
x plus 1. Two linear factors. So that
Two linear
means it
factors.
must look something like this, where a over x plus b over x plus 1. Multiply both sides by a denominator, we get 1 is equal to x times x plus 1. I'm sorry, a times x plus 1, and then b times x. Distribute that a,
Distributing the
and you have it to
ax
where
plus a plus bx.
a plus b is equal to 0 and a is equal to 1.
Because
If
there's
a is
no
equal to
x on the
1, a plus b
left.
is equal to 0, then b must be negative 1. So that
So I talked over myself. So a plus b is equal to 0 because there's no x term on the left. But a is the only numeric value without a variable attached to it. So a is equal to the only numeric value on the left, which is just 1. Which
makes
using that
this
first
guy
part means it'll be
1
negative 1.
over x minus 1 over x plus 1.
So a is 1, b is
So I
negative
can
1.
split up that integral over here. Sorry, I just noticed something. One of my
Oh,
timers is 15 and one of the...
so this is when I realize that something's wrong because for some reason the timer of the vertical video, this video right here with the bear, is different than the timer over here. But I'm not realizing that the vertical video by this point has crapped out. So just some fun BTS. Carry, keep going.
This timer says 21. Why the huge difference of time? Okay, we're gonna move on from that, I guess. I'll figure it out in post. Um, 1 over x minus 1 over x plus 1 dx. From here, we know the u substitution. Well, this doesn't have u substitution, but we know this u substitution for this is pretty straightforward. U
6
is
plus
x plus 1, du is equal to dx. So we have this to be ln of x minus ln of x plus 1. And then our final answer will have x squared over 2 plus 2x plus ln of x minus ln of x plus 1 plus c. And that is our final answer. All right, now from here, we're going to move on into the numerical integration. Now, um, let's see. So it's appropriate for us to go over different types of approximation methods for integration. The three that we're going over is the midpoint rule, the trapezoidal rule, and the Simpsons rule. They have some similar notations to what we've done in the past. So let's go ahead and go over them. First, compute the change of x. So we're going to look over an integral from some a to b. So we're going to go ahead and look from this a to b, but we're going to approximate it with n n subintervals. I accidentally wrote the n too close. Then we're going to go ahead and write out all of the pieces that we use for interval. We start with xo being a, and we're going to keep adding that change of x until we get to the ending b. Now 3 through 4 and 5 for some of these are different. They are going to abuse the midpoint rule. The midpoint rule here. The midpoint rule will use this step 3. The trapezoidal rule here.
Oh, I'm doing the highlighting. Okay, so this is part I'm doing highlighting. So midpoint we'll use this. Trapezoidal we'll use
The
this.
Simpsons rule here.
We'll use this.
Now the caveat of all of these is that this uses all of the terms as an input of the function, but only the middle terms, not the starting and ending point, will be multiplied by 2. And also we multiply the whole thing by 1/2. For Simpsons, we have this alternating pattern of 4 and 2, 4 and 2, 4 and 2, 4 and 2. Do not include the first and the ending coefficient. I mean, the ending inputs. And then the midpoints, use the midpoints for all of these. It looks very much like what
The Riemann
we learned
sums
for
our first unit.
what we learned for 1.1, the Riemann sums idea. And then let me see, is there any other stark differences? Not really. Yep. No. Okay, that's pretty much it. All right. So let's go ahead and let me write the more notations. F of x, dx. Okay. So let's go ahead and start off with all of these. So I'm gonna do number one. Number one for all of these will be the same. Oh, sorry. Question. Approximate this integral using all three rules. N is equal to 4 subintervals. Compare their errors. So that means at one point we're gonna have to do the integral itself as well.
You will.
I guess we'll save that one to the very end. Let's go ahead and do this one. So compute the changes of x. Well,
Good job.
we know that we are starting from 2. I mean, we're ending at 2, we're starting at 0. And I'm going to do 4 intervals. So this is just 0.5. Or 2 over 4, which is 0.5. And then all of our x's start at 0, and then it's just us adding 0.5. So x1 is 0.5. x2 is 1. x3 is 1.5. x4 is 2. All right, now we're going to do let's do the midpoint rule. Actually, for this, since I accidentally started for the coding, I might as well just color code the pens as well. So we have 3M. It says find the midpoint of each subinterval. So the first midpoint is 0 plus 0.5 divided by 2, which is 0.25. And then the second midpoint, which is 0.5 plus 1 over 2, is 0.75. The third midpoint between 1 and 1.5 over 2 is 1. Oh, so I guess. Okay, so the video crapped out, crapped out. Okay, 'cause the audio just ended. Okay, well I can finish talking from here. It was literally me doing the video. So, for the third midpoint, you go 1 plus 1.5 divided by 2 to get 1.25. And that last midpoint from x3 to x4, you add them divided by 2 to get 1.75. Afterwards, you're going to plug them all in. What I started doing at this point was I was like, okay, well, these are all fractions that are very easy to compute the square of. So I rewrote 0.25, 0.75, 1.25, and 1.75 as fractions respectively, squared them, and adding 1. And now you just use the fact that 1 is equal to 16 over 16. So, for example, 1 over 4 squared is 1 over 16. So plus 1, you just add 16 to the top, 17 over 16. Over here, 3 over 4 squared is 9 over 16. Plus 1, 25, because that's 9 plus 16. Over here, 5 over 4, that gets squared to 25 over 16, plus 1, 41 over 16. And then lastly, 7 over 4 squared plus 1 is equal to 49 over 16 plus 1. You add the 16 to that 49 to get 65 over 16. Afterwards, you're going to go ahead and do the midpoint where you add them all up and then multiply by the rate of change, which is 1/2. You'll get the fraction 148 over 32, which you input as, or which plugs in as this. Then for the trapezoidal rule, we just plug in all of these into the function. So 0, 1/2, or 0.5, but then I also was like, okay, well, 1/2 is easier to square than 0.5. So it's just 1/2 squared, and then same thing with this guy, the 3 over 2 squared. And let's go in there. So 0 squared plus 1, that's 1. 1/2 squared plus 1, that's 1 over 4 plus 1. I used the fact that 1 is 4 over 4 to get 5 over 4. 1 plus 1, 2. 3 over 2 squared is 9 over 4 plus 1, 13 over 4. And then lastly, because 4 is 2, so 2 squared plus 1, that's 4 plus 1, 5. Then we go ahead and plug them all in, but we multiply everything but the first and last terms by 2, and we multiply everything by the rate of change and 1/2. So that becomes 1/4. And then that over here, this gets simplified to 5 over 2. This gets simplified to 13 over 2. That's just 4. I went ahead and took advantage of the fact that I can just manipulate these. So I put these on one side and combine these to be 18 over 2. That's just, oh, I forgot to close that bracket, parentheses. That's just 9. That's just 10. So 10 plus 9 is 19. 19 over 4, 4.75. And then the last one for Simpsons, I just copy and paste all the functions since Simpsons dictates that we get all those values again. And now I just plug it into a different pattern, but this time with alternating 4, 2, 4, 2, which really we only have one instance of 4, 2, 4, not including the first and last term. And then we multiply it by the rate of change and 1/3. So this became 1/6. The denominator cancels out, so we're just left in 5, 13 respectively. 2 times 2 is 4. This all combines to 28. over 6, which is 4.666. I drew a little dash on top to know it's continuous. So those were all the approximations, but what about the actual error? So doing the actual integral, I get 14 over 3, which if you want, you can pause the video to just look through that. But you'll get 4 over, or you get 4 over, you get 4.6 continuously. Well, from here, we can see which one is the better and has the lowest error. Midpoint, if you do the math, you have about this rounded to 4 decimal places. For trapezoid, if you do this, this was just a continuous 3. And then for Simpsons, they're the same exact thing. So the error was 0. So Simpsons had the smallest error. All right. So this was a bit of a weird video, guys. I'm gonna be honest, if you think this warrants a re-recording, just let me know. I get it, especially because it's not 100% fair, but I did try to salvage it by doing this sort of forced audio dub. But if it just didn't mesh well, that's perfectly fine. I can adjust the schedule to where we can record this again. So that's no qualm on me. But just let me know if it worked. If it didn't work, then it didn't. Um, yeah. All right. Let me know if you guys have any questions. And now, because I did end the video before saying this, but now I'm gonna work on the worksheet video. So I'll see you all then. Bye bye.